At 11:30 in the morning on November 7, 1943, a young American pilot circled through thick cloud over France, fighting wind, cold, and failing navigation. He believed he was flying toward home, back to England, but the weather was brutal. The clouds stretched from low altitude up to 20,000 feet, and visibility inside them was almost zero. The fuel consumption rose faster than expected, and every minute in the air pushed him closer to a crisis. He had trained for combat, not for a storm that erased the world around him. When he finally dropped beneath the clouds, he expected to see the English Channel. Instead, he found farmland, buildings, and an airfield that looked friendly. Exhausted and running low on fuel, he lowered his landing gear, touched down smoothly, and opened his canopy to greet what he believed were Allied mechanics. German soldiers ran toward him with rifles raised. The pilot was stunned. In minutes, he was captured, transported to a holding area, and sent to a Luftwaffe prison camp where he would remain until the end of the war. His name was William Roach, and he was only 22 years old. But his capture wasn't what mattered. What truly changed history was the aircraft he left sitting on that field, a perfect, intact P-47 Thunderbolt. Germany had never seen one in functional condition before, and they had been trying to understand it for months. Wreckage from combat revealed almost nothing about internal engineering. But Roach's mistake had delivered something Germany desperately wanted: a pristine Thunderbolt that could be examined, flown, tested, and understood. The aircraft was immediately photographed, inspected, put under guard, and repainted with German markings to avoid being shot down by anti-aircraft guns. Then it was flown to Germany's most advanced aviation testing facility. The Luftwaffe had been fighting Thunderbolts for months and knew they were difficult to destroy, but no one understood why. Engineers had assumed the aircraft was clumsy, heavy, and inefficient. German fighters could climb faster, turn tighter, and required far less runway. On the surface, the Thunderbolt looked like a crude machine, even comical in its bulk. But combat reports showed the same unsettling pattern. The aircraft absorbed catastrophic damage, shrugged it off, and flew home. The first major revelation came when German structural engineers examined the fuselage. Their philosophy had always prioritized lightness and precision. German aircraft were masterpieces of weight optimization. Frames, spars, and skins used only the minimum aluminum necessary to maintain strength. Every gram saved translated into speed, acceleration, and maneuverability. Engineers measured forces carefully, calculated tolerances, and relied on the thinnest material that could survive expected combat loads. The Thunderbolt did not follow that philosophy at all. Its fuselage used aluminum nearly twice as thick as German fighters. Structural supports were spaced closer together, heavier, and designed with enormous strength margins. Wing spars looked like components taken from a medium bomber rather than a fighter. When engineers ran stress calculations, the results made them shake their heads. The Thunderbolt could withstand structural loads far beyond anything a human pilot could survive. The wings alone were capable of withstanding over 20 G before catastrophic failure. That number was absurd, unnecessary, and impossible to reach in real flight. German aircraft designers would have considered such reinforcement a waste of material. At first, the German engineers criticized the American design as inefficient and heavy. But after deeper evaluation, a very different realization emerged. The Thunderbolt wasn't designed to be elegant. It was designed to be built quickly by unskilled labor, repaired easily in the field, and survive damage that would destroy conventional fighters. Engineers had assumed the aircraft was clumsy, heavy, and inefficient. German fighters could climb faster, turn tighter, and required far less runway. On the surface, the Thunderbolt looked like a crude machine, even comical in its bulk. But combat reports showed the same unsettling pattern. The aircraft absorbed catastrophic damage, shrugged it off, and flew home. The first major revelation came when German structural engineers examined the fuselage. Their philosophy had always prioritized lightness and precision. German aircraft were masterpieces of weight optimization. Frames, spars, and skins used only the minimum aluminum necessary to maintain strength. Every gram saved translated into speed, acceleration, and maneuverability. Engineers measured forces carefully, calculated tolerances, and relied on the thinnest material that could survive expected combat loads. The Thunderbolt did not follow that philosophy at all. Its fuselage used aluminum nearly twice as thick as German fighters. Structural supports were spaced closer together, heavier, and designed with enormous strength margins. Wing spars looked like components taken from a medium bomber rather than a fighter. When engineers ran stress calculations, the results made them shake their heads. The Thunderbolt could withstand structural loads far beyond anything a human pilot could survive. The wings alone were capable of withstanding over 20 G before catastrophic failure. That number was absurd, unnecessary, and impossible to reach in real flight. German aircraft designers would have considered such reinforcement a waste of material. At first, the German engineers criticized the American design as inefficient and heavy. But after deeper evaluation, a very different realization emerged. The Thunderbolt wasn't designed to be elegant. It was designed to be built quickly by unskilled labor, repaired easily in the field, and survive damage that would destroy conventional fighters. German aircraft depended on perfect workmanship. Rivets, welds, and tolerances had to be exact. If something was slightly misaligned or struck in battle, critical components could fail immediately. The Thunderbolt did not demand perfection. If a rivet was crooked or a skin panel slightly warped, the aircraft still held structural integrity. If it took hits from cannon or machine gun fire, the massive frame absorbed punishment, and the pilot lived to fight another day. This discovery changed how German engineers viewed American industrial strategy. American factories could build complex aircraft in huge numbers without requiring years of training for assembly workers. The Thunderbolt was intentionally overbuilt, allowing manufacturing flexibility and battlefield survivability. German fighters could perform dazzling maneuvers, but were fragile machines requiring constant specialized care. The Thunderbolt was rugged, tolerant, and designed with wartime priorities in mind: simplicity, durability, and quantity. The next shock came from the engine. German engineers were loyal to inline liquid-cooled engines, sleek, powerful, aerodynamic, and mechanically refined. But they had one fatal weakness: damage to coolant lines or radiators meant immediate failure. Even a minor hit could doom a pilot. The Thunderbolt used a massive radial engine that seemed crude and agricultural. It weighed more than 1,000 kilograms and sounded rough at idle. Yet its toughness embarrassed Germany's most refined designs. The engine could lose multiple cylinders, lose oil pressure, and still operate well enough to get home. German test crews intentionally damaged it to understand its limits. They removed spark plugs from multiple cylinders, punctured the oil cooler, and even shot the engine with small-caliber rounds. Instead of seizing or exploding, the engine continued running with reduced power. A German inline engine would have failed immediately under similar conditions. The P-47 didn't win beauty awards, it simply refused to die. Then came the armament. The Thunderbolt carried 8 heavy machine guns, 4 in each wing, with over 3,000 rounds of ammunition. German aircraft carried less ammunition, trained pilots heavily in precision shooting, and expected pilots to make every burst count. American doctrine was completely different. Volume of fire made average pilots dangerous, and sheer bullet density created lethal strike zones. A 3-second burst from the Thunderbolt sprayed dozens of projectiles into a swath wide enough that precise aim became less critical. German pilots reported that entering a Thunderbolt's firing line felt like flying into a wall of metal. Damage accumulated quickly. The turning point wasn't just design, it was production. Germany still believed technical excellence could overcome numerical disadvantage. But in early 1944, American factories reached industrial output Germany could never match. Hundreds of Thunderbolts were produced every month, supported by thousands of trained mechanics and pilots. Replacement aircraft arrived faster than they were lost. Replacement pilots arrived faster than veterans were killed. That reality changed the air war. Pilot training illustrated the imbalance even more dramatically. American pilot schools offered hundreds of hours of flight time before new aviators ever reached combat units. They learned tactics, engine management, instrument flying, emergency procedures, and formation discipline long before entering danger. Roach may have made a tragic navigation error, but the system behind him ensured that another trained pilot replaced him quickly. German pilot training collapsed under fuel shortages, aircraft shortages, and rushed instruction. Some pilots arrived at combat units with barely 100 hours total experience and only a handful of hours in the aircraft they would use in battle. Many died on their first missions. Veteran losses could not be replaced fast enough, and the Luftwaffe slowly bled away its most skilled aviators. Meanwhile, American pilots who survived their first few missions gained confidence, refined tactics, and benefited from the Thunderbolts' ability to survive mistakes. Combat over Germany grew increasingly one-sided. Thunderbolt formations climbed high, used the sun behind them, dove at extraordinary speeds, and struck vulnerable German aircraft before they could respond. The P-47's firepower stunned even experienced German warriors. Many aircraft that survived initial attacks returned riddled with holes, their structures creaking and engines coughing. Those that didn't make it home often fell after accumulating cumulative damage rather than a single critical hit. Even when German engineers analyzed wreckage and identified weak points, oil coolers, control linkages, turbocharger ducts, the Thunderbolt's redundancy often allowed damaged aircraft to keep flying. Attacks that would instantly destroy German fighters merely slowed American ones. Every missed opportunity frustrated pilots already fighting against numbers they could no longer match. Eventually, a realization settled over Germany's aviation leadership. The Thunderbolt itself was not the true threat. What made it terrifying was the industrial system behind it. Factories that could build aircraft faster than Germany could shoot them down. Training schools that produced pilots faster than Germany could replace its dead. Supply lines that repaired damaged aircraft overnight. And a national economy capable of sustaining total war indefinitely. The captured Thunderbolt represented a profound lesson. The war was no longer about elegant engineering or pilot heroism. It was about logistics, manufacturing scale, and survivability. Quality machines built in small quantities became irrelevant when overwhelmed by vast fleets of rugged, good-enough aircraft supported by endless replacements. Germany could shoot down 10 Thunderbolts, and 20 more would arrive by the end of the week. Years later, German engineers and test pilots admitted that they misunderstood the American approach. The Thunderbolt had been dismissed as crude because it didn't fit their design philosophy, but it embodied a strategy that made perfect wartime sense. It could survive damage, extend pilot life expectancy, accept imperfect manufacturing, and operate in environments that would cripple more refined aircraft. And most importantly, it could be built faster than the enemy could destroy it. The now-forgotten navigation error that led to the Thunderbolt's capture did not change the war. By the time Germany understood every bolt, spar, and engine component, thousands more had already entered combat. The Thunderbolt proved that wars are not won solely in dogfights or by tactical brilliance. They are won in factories, supply chains, training bases, and industrial production lines capable of replacing losses faster than they occur. The aircraft wasn't the best individual fighter of the war, but it was the fighter that arrived in such overwhelming numbers that opposing brilliance couldn't survive. In the end, the Thunderbolt demonstrated an uncomfortable truth. Technological perfection means little if the enemy can build unlimited machines that are rugged, survivable, and flown by pilots who learn quickly. Germany fought skillfully, but it could never compete